of course, when we solve the eddy current problem, we need to be aware of eddy currents and the skin effect. This is already important in the design stage of the model, since the skin or penetration depth have to be appropriately resolved by the finite element mesh. So what are the ingredients for the eddy currents? Of course, we need a conductive body, so the conductivity must be non-zero, and a time-varying B field. And by the rule of Lenz, we know that the change of a magnetic flux through a conducting loop induces a voltage leading to a current in conducting bodies. And these arising eddy currents result in the B field against the original B field. Furthermore, we know that we have a current density increase at the surface of a conducting body. So if you have a conductor and you have an alternating current flowing through it, the eddy currents will lead to a current density concentration at the surface. So what we need to know for our design of the finite element model is what the skin depth is and how can we approximate it. So, of course, for this we need governing equations in order to get the estimation of the skin depth. We'll just recall them. So we have Ampere's law, we have Faraday's law, and of course we have the constitutive relations. And as we do for obtaining the eddy current problem, the displacement current density, so the time derivative of the D field, is neglected. We'll do a further simplification in terms of geometry. So we'll consider the solution for an infinite half plane. You see it here. We have the boundary here at z equals 0. And then we can write Ampere's law in this one-dimensional form. We only have the partial derivative of hy, the y component, so the one pointing into the plane with respect to z, and this must be equal to the current density in the x direction. For Faraday's law, this is similar, and so for the constitutive equations, also they become one-dimensional. And now you can combine this equation to obtain a diffusion equation, equation 46, which models the diffusion of the electromagnetic field into the conductor. And of course, you can obtain a solution for this diffusion equation. I'll just highlight briefly here how to derive this solution. So first we'll do a harmonic ansatz. This was a linear equation, so we can do this. So we introduce this ansatz for the harmonic time dependence, and we keep the spatial dependence in the amplitude coefficient, hy, with a head here. It can be complex valued. We'll insert the ansatz in the diffusion equation and see, okay, time derivative is gone. We only have derivative with respect to z. And for this equation, ordinary differential equation, we have to solve the characteristic equation. So we can get the two roots of the characteristic equation and plug them into the general solution for this differential equation, which is simply given by the exponential functions with the roots in the exponent. Now we have to satisfy the boundary conditions, so we have to look at the value for the coefficients. And actually physics tells us that the magnetic field needs to decrease with the distance z, and therefore the coefficient C1 needs to be 0, and we only end up with the coefficient C2. Additionally, we can do some math and take the square root of j to rewrite the expression, and we can also use the boundary condition at z equals 0. We want to have the H field H0. So this gives us the second coefficient and the final solution for this equation. This is now written in the complex domain. However, and we can simplify it a little bit. So we plug this in the original ansatz, and then we see that we can introduce this parameter delta here, which is called the skin or penetration depth. And we see it is frequency dependent, and the real physical magnetic field strength is actually given by the real value. So this is the complex valued amplitude, and we can write it as the real value using the cosine, for example. And we can see here the amplitude of the cosine is actually decreasing with the distance, and the parameter for the decrease is set over delta, where delta is our skin depth. So this is a length dimension. The expressions for the B field and for the J field and the E field, of course, follow analogously, and so they have the same expressions. Let's have a look. So all of these fields decay exponentially with the skin depth. Note that also there's a phase change. So in the cosine, we also have set over delta. So at some depth, the field quantities even change directions. And this is actually very similar to a boundary layer, or this is a boundary layer problem. And therefore, we need to take special care when we mesh our finite element model and also choose the ansatz functions. Just as a guideline, we should resolve the skin depth with approximately 10 degrees of freedom. And as this is an exponential decay, which is smooth P refinement, so refining the order of the ansatz functions by increasing it will be beneficial.